Okay, we're recording, so let me hand things over then to group 3 to present their CSD design.
Hello. So we are Alex Bailey, Sam Fetter, Andrew Graber, Josh McHarris, Marco Moreno, and Elio Porto. And this is our design, the G3 CSD, and we are part of the James Industries. So just a bit of an outline of our presentation. We'll start off by talking about our hedgehog concept and our mission. We'll do a little bit of overview of the design, and then we'll go into an analysis of each of the subsystems. And then we'll go into a cost breakdown, and then we'll talk, kind of review everything, a little bit of a summary, and we'll go into some questions at the end. So here at the James Industries, we strive to create and advance space exploration. So through the extensive analysis of each of our subsystems, we've created a unique product that creatively satisfies the needs of our customer. Our goal is to ensure mission success along with a cutting-edge CubeSat dispenser design. So just over here on the right, kind of our hedgehog concept. So our passion is advancing space exploration. Economic viability is mission success, and best in the class at a very detailed analysis. So just going over the outer dimensions of the CubeSat and the overall mass. So it fits in the correct frame. So it's 349 millimeters by 347.3 millimeters by 493.5 millimeters. And the overall mass is less than the 5 kilogram threshold at 4.98 kilograms. So just a bit of an overview of the subsystems. So we have the door mechanism, and then we have a dispenser mechanism, the overall frame or box, the CSD control, and then the launch vehicle electrical interface. So going further into that, and we see our design here on the right-hand side. So we have a rail-guided dispenser, as you can see on the bottom of the CubeSat dispenser. Two-spring dispenser, which is seen kind of back in the Z face of our dispenser. The pin puller mechanism, which is seen on the top of the CSD. We have a door locking spring mechanism, which the torsion springs allow for the door to open. We used aluminum 7075 T6 for almost the entire frame with hard anodized rails. We have limit switches that show the door occupancy state, and a DB9 launch vehicle connection that connects the launch vehicle to the CubeSat dispenser.
Okay, so first we're going to go over the door mechanism. And quickly summarize some of the customer needs that were critical to door mechanism design. The first was the structural load environment. We were required to actually support 7.5 Gs. So one way we achieved this was by designing the pin puller to withstand that force in the axial direction. The next need was the mass requirement. So we had to be below 5 kilograms. The final mass of our door mechanism ended up being 0.91. And finally, door reliability. We were required to open the door in less than 2 minutes. Using our torsion springs, we were able to achieve this in about like 2 seconds. So to quickly summarize the door mechanism, we implement a pin puller to pin and unpin the door. The pin puller is mounted to the main frame housing, and the actual pinhole tab is on the door. We use torsion springs to provide the torque to open the door once it's unpinned. And we designed the locking mechanism just down there at the bottom between the two hinges that restricts like rotation past 90 degrees. So to determine the necessary forces we needed for the pin puller, we took the actual requirement to support the 7.5 Gs. So we took the mass of the CSD multiplied by the 7.5 Gs and the gravity constant, and we added that to the force of the spring because all of that load is on our door. So we modeled the door as a simply supported beam with just a singular point load. Solving for the reaction force at the pin gives about like 2,300 newtons. This is the necessary side load that the motor has to be able to handle. And then to determine the pulling force of the pin puller, we can find the frictional force between the pin and the pinhole tab. The pin of the pin puller that we ended up going with is coated with Tylon PTFE lubricant. So it drastically reduced our frictional force. The resulting frictional force was a little over 200 newtons. You can see the specs of the motor in the table on the right, and it's able to handle all the forces. So to properly size our torsion springs, we modeled the torque to be able to basically provide enough torque to counteract the force of gravity on the center of the mass of the door. In terms of the actual wire diameter of the torsion spring, designed for 60% of the yield strength. So using that equation seen there, we can find the wire diameter as well as the corrected stress using like a corrected constant. So our final spring properties can be seen in the table. We designed for the deflection to be 270 degrees. The spring rate was 1.63. It was designed for an 8mm shaft diameter, and our final wire diameter is 1.5 millimeters. So we needed to determine whether or not that 8mm shaft could handle the actual loads and not shear. We determined the reaction force at that hinge. So between those two arms, each hinge had to handle about the 2,300 newtons. Using the max shear strength of the stainless steel shoulder screw, we could determine the minimum area. And from that, we determined that the diameter is about 2.5 millimeters. So therefore, our 8mm shaft is plenty strong enough to handle the load. So to determine door thickness, in this case, we modeled as a simply supported beam again, but with 2 point loads. So at each point load is where the CubeSat rails would come in contact with the front face or the inside face of the door. So using the moment of inertia of the door and the max moment, we were able to determine the stress with a 2mm thickness. The resulting stress was 162 MPa. And then this is, there you go back. Okay. This is well under the yield strength of the 7075 T6 aluminum. So the spring-loaded locking mechanism, once the door opens past 90 degrees, the spring-loaded pin on the bottom edge of the door, it pops into the key housing. So that the D-shaped pin, once it rotates to the certain point, the geometry allows it to the spring to extend. We designed this in order to prevent the door oscillating or possibly bouncing back up. So we are able to limit the ejection interference with the CubeSat launch. And then finally, we performed a quick vibrational analysis. We determined the door resonates at about 130 hertz. This is above the allowable threshold. And then the maximum displacement found was about 0.1 millimeters. And we did this all in SolidWorks.
Okay, so moving on to the dispenser launcher subsystem. The main principal customer needs that were used in the design were customer need C2, which speaks on the structural load environment and how the design must be able to survive the most stringent loads. Customer need C9, which attempted to minimize the total mass of our CSD. And customer need C19, which set our initial velocity to be anywhere from 0.5 to 2 meters per second. Although in all of our design, our target velocity was 2 meters per second, as explained in the team interchange meeting with our customer. So a quick overview of our launcher mechanism is that it implements a dual spring injection design, which incorporates a push plate. And this push plate is what transfers the elastic spring force to the CubeSat and launches it out of the CSD. We're able to secure the springs using spring mounts that we extruded out of both the push plate and the attachment plate, as seen here on the figure. And we attach those using, these bars, which are bolted on to these spring housings. And lastly, we implemented a design of using guide rail guards, as you can see at each corner of our push plate. These guards essentially help to maintain the push plate in alignment in case that it tilts or possibly gets stuck. So the subsystem integrates with the rest of the assembly using the attachment plate as seen in the top figure. This attachment plate is bolted together with the back plate of the frame using M4 by 0.78 millimeter bolts. Once again, the guide rail guards prevent the push plate from tilting and help it achieve a more linear movement as it pushes the CubeSat out of the CSD. And like I said earlier, the attachment bars tighten down the first coil of the spring. And once these are tightened down, the spring is secured and won't be able to move out of that spring housing. So the first thing we did to filter down our search for viable springs that achieved the requirements that we needed was to first make sure that they survive the most stringent loads. So once we were able to filter down to a certain amount of springs that are able to survive that certain load, we use a conservation of energy approach to make sure that the compression length that we needed to compress the springs in order to release the CubeSat at a velocity of 2 meters per second wasn't more than the suggested max deflection by the manufacturer. So once again, we used the conservation of energy approach where we made equal the kinetic energy as well, equal to the potential energy, and having the spring rate of the desired spring, we were able to calculate how much we needed to compress it to reach that target velocity of 2 meters per second. So once we iterated through a certain amount of springs, we chose one that made the most sense to our design in regards to its free length and compression length.
Moving on to the frame, some of the customer needs that we were really focused on when designing it was the structural load environment, which is enveloped by a 4.1 G, which we achieved with a factor of safety of 1.4. We were looking to minimize the mass, minimize the production cost, and satisfy the vibration environment requirements. The first iteration of the frame had its flaws, and in this current version, we were able to solve a lot of these things by optimizing different dimensions and supports. So some of the issues, this design was really heavy. The panels on the side posed huge vibrational risks, and it didn't have any radiation protection or and its factor of safety was far too high. The design that we have now is composed of 2 parallel plates connected by 8 rods. We elected to ditch the rods that we had from the previous design just because of the redundancy that it posed with having rails and rods supporting the frame. So now instead we just use 8 rails, which we also use as supports that guide the CSD payload or the CubeSat payload. Then on the outside of that, we have 4 panels. This helps with radiation shielding, provides tensile support for the outer surface, and helps attenuate the vibrations induced in the rails. So when we were selecting material, we used Ashby plots to kind of narrow down our search to figure out what we needed. We used mom calcs to pretty much figure out the yield stress that we needed. And then we had all of these different viable options. And from that, we compared them: cost, density, thermal expansion. And we were able to figure out which material that we wanted to use. Which brings me to my next slide. So we picked aluminum 7075 P6. It's used for the entire frame, but the process that we used to select the material for the frame was also used for a lot of the other subsystems. We didn't want to outline every single material selection for each subsystem, but they kind of followed the same principles. So yeah, it has a really high strength to density ratio. It matches the thermal expansion of our customers' rails, which was a big deal. And yeah.
So the driving scenario, like the worst case scenario that helped us to determine the geometry of our overall cross section of the frame was basically a cantilever beam where we're mounted on that -Z face, and the forces are going in the -Y direction. So we model it as a distributed load under the acceleration of launch. And basically we set an allowable deflection for our frame based on the gaps between our rails and the customer's CubeSat. And then using that, we solve for the minimum necessary cross-sectional moment of inertia, I. So using the fixed parameters of distributed force, the allowable deflection, and the material of the frame, our minimum cross-sectional moment of inertia was 9.62, as seen there. And then we designed for a factor of safety of 1.4, which led us to our current dimensions, which result in a moment of inertia of 1.35 times 10 to the 6 millimeters to the 4th. Moving on. So while deflection was like a driving factor in our design, we also went to evaluate the maximum tensile stress on the outer panels, again, using that beam bending calculation. So the stress was found as My/I, and the maximum stress on those panels was found to be 4.59 megapascals, which is way under our yield stress for the material, 500 megapascals.
We also performed some vibrational analysis. So the first thing that we did was find the resonant frequency of the entire CSD, which gave us the frequency 191.78. And we saw that it fell on the top panel of the frame. So analyzing that, we put in, well, First, we looked at NASA guidelines, and we saw that the over 100 hertz falls outside of the envelope for the sinusoidal input frequencies. So we elected not to perform a dynamic analysis for the sinusoidal inputs, and rather we just performed a random vibration test. So we set the domain 20 to 2000 hertz, which was provided from the launch vehicles. And then we had a resultant displacement of 1.335 millimeters and a stress of 179 megapascals. Neither of these are concerning because it won't cause any interference, and it has a factor of safety of approximately 3.
I'm muted, sorry. The overview of the CSD control and electrical interface subsystem customer needs that we focused on were the thermal environment, in which we ensured that all electrical components could withstand the range provided by the launch vehicle mission guide, the electrical bonding between the launch vehicle and the CSD, which we met with a small contact resistance of our DB9 connector, which is off the shelf, and the operating voltage requirement, which meant that all components have to operate on 28 volts. We also supplied a door state or door status signal to the launch vehicle, which accomplishes our customer requirement of status communication. So an overview of the subsystem here for CSD control, we have 2 limit switches at the front of the frame, which will determine the door state. And then the pin puller is directly wired to the DB9 connector, which goes to the launch vehicle. For the launch vehicle interface, it's just the DB9 connector. So that's where, can you go to the next slide? Sorry. Where the launch release signal will be sent to the pin puller through pins 1 through 2. And then that's how we'll also communicate the limit switch status and then properly meet our grounding requirements. So that DB9 connector is on the -C face of the frame, and it's inset, so it doesn't provide, or it doesn't have any interference with a flat panel that the CSD would be mounted to. As far as cable routing, the cables are held in place with nylon clips, and they're also sleeved in an abrasion resistant nylon sleeving, which would help prevent any failures due to sharp edges on the frame or any damaged connections. And so these connections go to a cavity in the back plate, and that front face of the back plate is covered by the dispenser attachment plate in the spring subsystem.
Okay, moving into cost breakdown of the CSD. This is the cost breakdown for 1 unit. So we took into account cost for OTS parts, raw materials, energy usage, manufacturing labor, assembly labor, and design team salary. For manufacturing labor, we calculated that using the process costing tables and the multipliers given to us. And assembly labor, we use an average hourly wage for an assembly worker along with the assembly time we calculated for our assembly. And the design team salary, we use a average salary for a mechanical engineer, but only for 6 months. And the table on the right is the cost breakdown for every single custom part we have in our CSD. And all of these costs combine into a total cost of $280,549, which is well below the $500,000 requirement. This is the cost breakdown for a production scale run of 100 units. The total cost for just the OTS parts and raw materials take into account bulk ordering. And due to this, we have a savings per unit of $818.92, which means the CSD itself, just 1 unit, costs around $279,000. And for the manufacturing labor, energy, assembly labor, and just those 3, we multiplied those by 100 for the 100 units. And to the left, there's a pie chart visualizing the entire cost breakdown for the production scale run.
So in summary, we believe that our CSD design has met all of the customer needs as featured in earlier in the report. As we went through the subsystems, we were able to kind of go through and talk about the customer needs and what each subsystem met best, even though a lot of the subsystems ended up meeting multiple different customer requirements. We really only featured in the presentation the ones they fit the best, but we believe that our CSD design has met all customer needs. And on top of that, we do believe that our unique features of a locking door with torsion springs and a rail-guided multi-spring dispenser system make our design very attractive and unique for selection. So I just want to go ahead and thank everyone for coming and listening to our presentation. And I hope that everyone enjoyed watching our presentation and our design choices. And we're going to open up the floor for some questions.
Cool. Oh,
Hi there. Dr. Tom, do you have some questions first or?
yeah, I do, but go ahead.
Hey guys, great presentation. I wanted to ask you guys about a couple of things. Particularly, I wanted to ask about the vibrational analysis. You had the door earlier, and then you had that slide on the vibrational analysis. Can you guys go back to one of those two slides? All right, yeah, so let's take a look at this one. So when you guys are talking about factor safety, you guys are talking about the deflection, right? That it's showing in the results.
Yes.
Okay. So
Or
the thing,
sorry,
Yep.
the factor of safety is based on the yield stress.
the yield stress. Okay. So the thing is, modal analysis is that you're not actually using modal analysis to figure out if something's going to fail due to the values produced from the results. You're getting modal analysis in order to see if it's matching modes, to see if it's matching frequencies, to see if it's going to run into issues where it's going to experience resonance. And it's difficult for you to do that if you're doing it just with one component at a time, because that's not how it's going to experience resonance. It's going to vibrate with that entire CubeSat structure all attached together. So doing it one part by one part doesn't actually give you an accurate vibrational frequency that it's experiencing. It won't give you an accurate displacement. So, you know, I understand that what you guys know in terms of vibration analysis is like limited at the moment, but for future iterations or future work, you're modeling these vibrations with the entire CSD in mind, not just with one, because otherwise it's not producing accurate results.
Right. So the resonant frequency that we got for this this top panel, the 191.78 was modeled with the entire CSD. In order to conduct the random vibration analysis, though, it was too memory intensive to run the simulation on the entire CSD, i.e. SolidWorks kept failing.
Okay.
So after that, we were looking to try and get a number for displacement, or like try to see where, like, what kind of issues would rise. So after that, we used base excitation on just one panel to perform the actual analysis.
Okay.
But that resonant frequency is for the entire CSD.
Okay, so you know it's probably would have been better if you guys left it there, because the result for just this one panel, looks like you guys have are all those green points, are all those what's it called, boundary conditions, fixed constraints at those points?
Yes.
Yeah, so that means that you're completely limiting movement. Like while you're trying to imitate the kind of fasteners you have holding this thing together, it's not going to be, you most likely over constraining your system and giving yourself results that aren't actually representative. It was a good idea with your limitations, considering again that your SolidWorks, your student version is limited in terms of capability. You know, and it's difficult to run a full analysis without having a lot of memory. But yeah, probably best to kind of leave in there and work off of those results rather than moving forward with this, which isn't really giving you results that are actually meaningful.
Any other questions?
Yes, there are many. I was just waiting until if Mark wants to say anything else. But while he's waiting, can you tell me, I might have missed this, but what is the weight of your whole design? The mass?
It's 4.98 kilograms. It's in the top or the front slide, like the first slide or second.
4.98. That's really close to 5.
Yes.
And I assume that does not include. What does that include?
So it
Everything inside
includes
the-
all parts in the SolidWorks as well as fasteners. It also includes weight for the cable sleeving and like all the off-the-shelf components.
Okay. All right, that's good to know. And still very close to 5, but I'm
Yes.
glad that it's below it, which is surprising to me, knowing that you've used a heavier part of aluminum. Aluminum 7075 is much denser.
Yeah, so
it is surprising to me, but
yeah,
I'll do
it was a big challenge to reduce weight. But basically a lot of our panels are very thin. And we tried to make cutouts like in the dispenser assembly where we have features that aren't really supporting any load or not critical, like we cut dimensions away.
Okay. On that note, since you said you've cut out materials and stuff, how are you depressurizing your cubes, your seeds?
So it's not a fully enclosed like pressure vessel. There's gaps in the panels on the corners as well as in the front door.
Okay. So
Yeah, this
if-
angle is a little bit like misleading. There's gaps in the rails there in the corners.
Okay, so if there are gaps,
Yes.
first, how are you preventing how are you going about cleanliness requirement that talks about nothing can go out in space and also inside? That's number 1. And number 2, how are you making sure that the inside temperature is okay for all of your electronics to use?
Yes, so as far as the cleanliness and like foreign object debris, during manufacturing, you'd want to put big emphasis on making sure that we load down every bolt and screw, but we don't have any like freely moving like debris sitting inside of the CSD that might exit the CSD and contaminate like any other launch vehicle subsystems. So we did not see that as like a huge driving need.
Okay. What about my
And-
second question?
Yeah, so the second question you said was, sorry, could you repeat again?
Yeah, so the inside temperature, how are you
Okay.
making sure that it is okay for your
Yeah,
electronics to work?
So all of our electronics were based on just the overall temperature envelope of 5 degrees Fahrenheit to 130 degrees Fahrenheit. So we did not model this as shielding any electronics inside, but all electronics were able to withstand that range of temperatures provided by the mission guide. We do not have a microprocessor or any other like sensitive sensors. Our main sensors are just limit switches, and the pin puller is something that has been proven on like multiple space applications and aerospace applications, and its temperature is way above the range required.
All right, I'm pretty
It's
sure, yeah.
below as well, right? Because once it's in
Yes.
space, it's also going to be pretty cool.
Yeah, like above the range, like, yeah, sorry.
Yeah, I guess my concern is with those gaps that you have in there is essentially no control of what your temperature is going to be inside. And in space, when it is, let's say, really cold, like, I don't know,
Yes.
minus 200, 300 Fahrenheit, what is like your method of preventing your electronics from basically freezing off?
We based our like temperature range on the like secondary payload metrics for like NASA's like launch document. So we did not design for that.
Okay.
Yeah, I think that range like encompasses like the interior part of the rocket where we'll be launching the CubeSats.
So you're essentially depending on your like for launch, you'll be enclosed in your
Yes.
deployer, but once it opens up to actually allow for the CubeSats to leave, that means it's going to be encountering the full cold of space. So definitely want to make
Okay,
sure these materials
understand.
and these electronics are going to be fine. I know you don't have that many electronics inside of
Yes.
your system, but that cold
And-
means also possible shrinking of materials and whatnot.
Yeah, I mean, I can go back and look at that, but the range for electronics was pretty wide. It wasn't just the 5 to 130. And our when we spoke to the customer, they said that their CubeSat itself was not sensitive to that temperature fluctuation.
Okay, so you're not worried about any problems with contact at the rails due to your CSD possibly shrinking and causing
Yeah,
issues
so
around that area?
the CSDs, all the frame components are built out of the same material as the customer's outer rails. So when we did the linear thermal shrinkage from like room temperature to space, they shrank at the same rate. And we also have provided a small minimum gap between the rails and their maximum dimension, which would allow us to still deploy the CubeSat.
Oh, sorry, I just interrupted. You just said, did you just say that the the CubeSat and the rails are the same material?
Yes, so when we spoke to the customer in the technical interchange meeting, their outer rails are made out of 7075 T6 aluminum, and all of our panel materials, all of our framing materials are also made out of the same material.
Have you heard of such phenomenon called cold welding?
Yes, so I think Graber went over it a little bit, but our rails will be hard anodized.
Okay. Okay, can you go next to when your door is open to the slide? Oh, right here. That was either this one or the one before. I think might be easier to see. Yeah. So what are those sticking out? I assume wires.
It's just like a factor of the SolidWorks model. In reality, the torsion spring would be deflecting and moving in the opposite direction. So it's held in place by the frame. Like it would not move out like that. It's just a factor of us rotating the door assembly.
Okay. So you're telling me in real life, it's not going to stick out.
Yes.
Okay. All right. Good. I was a little bit concerned about that, especially when the CSD is supposed to come out.
Yes.
All right. Another question I have is about springs. So it's good that we have them here. You only have 2 springs and they are centered. What is stopping your design from basically like rocking back and forth? Oh, like angle on a little bit if more weight is shown on.
Elliot, do you want to take that? Could you move forward in the slides to the dispenser subsystem?
Right. So we, for that exact concern, we implemented a set of guide rail guards that you can see here on the push plate at each corner of the push plate. The idea is that if the push plate, like you said, is to be tilted or not follow that linear motion that we expect it to, these guide rail guards, which will then be in contact with the rails and prevent that tilt or that rotation of the push plate.
Okay, Mark, do you have anything to say about this?
How is that plate manufactured? Are those like pieces? Are those things at the corners attached separately, or
no? It's all CNC machined from a single block, because
the
overall height would also encompass the housing of the springs, the circular housings there. It is not very efficient in terms of wasting material, but it does accomplish our need.
Okay, cool. Would you, in terms of the rails, how much millimeters of, or I got millimeters of contact do you have between the CubeSat and the rails, I guess, and then this component? Like, what's the width of contact that you guys are working with?
Looking at it from this direction, are you talking left to right?
So you have your rails, and I'm assuming they're touching on both of your faces. That
yes.
So what's that width that you're actually in contact with in the rails?
5 millimeters.
5 millimeters.
The CubeSat rail dimensions are 8.5 by 8.5, but they're centered. Our rails are centered to their dimension.
Okay. And then in terms of your actual movement, in your inside geometry, there's nothing that the CubeSat could possibly hit. Have you guys designed with any external components in mind of the CubeSat?
We did provide, so the overall CubeSat dimensions are 226 by 226.3. And they did ask that we leave an overall like external components of 240 by 240 because they have solar panels on the side of their CubeSat. But the front like orifice of the frame accounts for that. And there aren't any components that infringe on that 240 by 240 dimension.
How do you plan on letting the CubeSat access some of its side panels during a initial packing? Because like it seems like that when you put the CubeSat into your deployer, the only way to access it again would be to take it out, which is not ideal for a system that once it's in really shouldn't be taken out before flight. Do you guys have any mechanism for that?
We don't have
one
any
option.
mechanism, or you can talk about it.
Sorry. One option that we do have is the CSD has the side panels that are bolted on. So if it was really necessary for the customer to access their CubeSat, the panels could be removed without triggering any of the steps to launch or taking it out.
Yeah, it wouldn't have to be fully disassembled. It's not ideal because it's like 20 bolts. But if it were absolutely necessary, we could provide that access without like fully disassembling everything. But we would ask that our customer or our aero team do all the steps that they need to before loading it into the vehicle.
Yeah, unfortunately, like there's at least one step that they'll have to do like inside the vehicle, and this is just for y'all's information, where essentially for any electronic systems they have on the CubeSat, they're gonna probably have a remove before flight pin that is normally grounding that entire system away out when it's outside of the deployer, but once it's inside, will have other systems to ground it, and they'll have to remove that pin. And so you will probably have to have that panel taken off, but that also means that just in terms of assembly procedure, you'd probably want to leave the Loctiting of any bolts you have there until after you put that panel back on. Otherwise, you're going to mess up all the Loctite.
Okay.
But
Appreciate the clarification.
yeah, Julian, I think you had a question.
I do have a question. So you said that there is some space in your CSD that you left because of their solar system or the solar panels and stuff. What is keeping your springs compressed?
Do you want to talk about that?
Right. So the springs are compressed and during loading of the CubeSat, and that energy is stored while the door is closed. So the door itself acts as the stopper for the CubeSat, and in turn the spring.
Okay. I am slightly, maybe not slightly, concerned about that. You just said that there is going to be solar panels on top, and if you're putting a lot of pressure on it, and you play.
No, they're on the side, so they would be on
Okay.
the positive and negative Y face, and we'd contact them on the positive Z face. And their rails also stick out from their CubeSat, so we'd contact them at the 4 points of their rails and not on any like panels or instruments that they have.
Okay.
Right.
I'm still concerned.
Okay. Yeah, I could add more to what Josh was just mentioning. So during our team interchange meeting, this exact concern was brought up, and the customer, the aero team, explained that this will not be I guess not such a major concern for their design. As Josh explained, they have those they have their rails acting sort of as like bumpers in a way.
Okay, so basically what I'm hearing is you're placing it with the door constrains the motion and keeps the springs compressed. And the second the door starts to open it slightly, the springs are going to start to basically uncompress, release themselves, grinding themselves on that door. Not the springs, but the CubeSat. Can your CubeSat actually survive that?
I mean, if it can survive the actual compression holding the door, then it's fine in that moment. And
so do you know if it can survive the actual compression holding the doors?
I don't know their exact number off the top of my head, but I could confirm it with them. But their like rail subsystem is also built to survive the like 4.1 Gs of load.
I guess a better question would be, do you guys think that your door can open fast enough that the springs don't activate, the springs don't try to completely push out your CubeSat first? Because you guys mentioned, you got calculated how long it'll take for your door to open.
Mhm.
And if your door's not opening quick enough, that means that your CubeSat's going to start hitting your door. And you're going to lose some of the speed that you're trying to get from the springs.
Yes, we understand that. We had attempted, Simon had attempted to do basically size it to go faster, but it's pretty instantaneous. But the resistance from the door is minimal because the weight is pretty minimal, as well as there's no like gravity acting on it in space. Additionally, like our velocity cannot be confirmed at this moment to be exactly 2 meters per second, because there might be a little bit of friction. There might be a few other factors, but the like inertia of the door is not significant in reducing that velocity.
Okay, so generally you're saying that the door is gonna not be an issue, that it's gonna get out of the way before the springs really start to accelerate the CubeSat out?
Yes. Yes, because I forget the exact number. What was the time it takes to open, Sam?
In terms of like just the spring force, it was like a little less than 2 seconds.
Less than 2
Yeah.
seconds.
But
And-
it'll be faster than that also because if that force of the spring push plate on the door as well.
And also the torsion springs are sized to account for like the mass, the rotational mass of the door. So the force we would lose is like kind of counteracted by the torsion springs on the hinges.
Okay, yeah, I'm just particularly worried because of the fact that you do have a fairly fast time to open the door, but you also have some pretty strong springs underneath that CubeSat. So, it's kind of a question of which one really starts to happen first. And there's a possibility of the CubeSat actually hitting the door on trying to get out. And I don't know if you guys have anything to make sure that the CubeSat won't be the one to really push the door open.
Yeah, so the CubeSat will definitely contact the door. But we would have to confirm like the actual results through testing. But again, the CubeSat doesn't have any sensitive components where it will contact the door.
Okay. Yeah, that's something definitely to look at, because you don't want to drop your speed there.
Yeah, to actually qualify the system, we'd have to actually like build the whole thing and.
Oh, of
test it
course. No,
live.
there's you can't get through any mechanical system without testing, that's for sure. So there was a point where you guys mentioned a 1.4 factor of safety. If you guys happen to remember where you mentioned it, I just wanted to ask where you guys got that 1.4 from.
So we scoured the internet looking for industry standards that we could find from either CubeSat or CSD developers or NASA. And we found this came from a document that was pulled from an old NASA standard. It's taken away now, but we found it on a university website. And so we use that for our design factor of safety. Okay.
So to be honest, that's pretty good factor of safety. That factor of safety is at least in my industry right now, we're using that more for like ultimate strength for components that are they're planning on doing they already have more loads that they've already been able to include and consider in the result. For your system, where it almost you guys are still kind of like confirming that this thing's actually going to be able to survive, slightly higher factor of safety of 1.5 would probably be useful, and or using even an ultimate factor of safety, looking at the ultimate stress and making sure that one is also good, which will be maybe factor of safety between 2 and 2.5. But no, that's a good factor of safety to use for yield.
That being said, I don't see anywhere mentioning any shock loads and shock analysis.
Were you want to touch on that?
Yeah. So we went through, there was a NASA document that talked about different it was talking about acoustics as well as
I have a
shock,
problem.
mechanical shock. And the document basically said for acoustics that it was that CSDs have small like surface area, and because of that they don't absorb as much, and that the main failure mechanism or the main concern is random vibration. And then for the mechanical shock, it's, I believe it was something similar, but they did say that you should test it before. I mean, clearly it needs to be tested, but yeah, it's not usually a huge concern for the, well, this was a document about CubeSats, but we kind of applied it to the CSD considering that they're pretty related. But the shock, since everything is so light, I don't know, it kind of just I don't know, it was just a lot of testing. So yeah.
Right. Well, I'm looking right now at the document that we provided to you in Canvas with shock, and there is a considerable shock that can occur based on their natural frequency. That being said, you needed to calculate the natural frequency, correct, and do all of those to figure out what kind of shock environment your frame is going to be in. But more or less, you need to consider shock. It will happen.
Yeah, we did get a natural frequency, and we looked to do a shock analysis on SolidWorks, but the student version doesn't come with it. After that, we saw that a lot of times it's just a testing, like you can confirm it with testing. So that's what we were looking to rely on.
Yeah, okay. And if you could go to your sorry, your cost slide. Okay, so I am mainly thinking about how did you calculate the raw materials specifically?
We just from the PO, like over the materials we ordered. Yeah, just from the PO, like from our purchase order from the website, the manufacturer. So we're
And
gonna,
like for each individual part, we estimated that as a separate like plate or a separate stock. So we wouldn't be doing that cutting in-house. So we oversized our stock dimensions for the removal of material.
Okay, yeah, that's what I wanted to hear. Sometimes groups tend to just take the final result and put it in their cost, but I'm glad that you didn't do that.
Yes.
And I think Dr. Trum had the questions.
Oh, well, you can ask them too. While we're here, I was going to ask about microsense. I don't know if you did that. I don't think so. No. Okay. $8,719 and 15.36 cents. Boy, that's awfully precise. I feel like I'm driving to a gas station and paying 9/10 of a cent per gallon on gas. So, why all these extra significant figures, significant digits in your cost breakdown?
It's likely just a factor of like bringing it in from the Excel that we didn't properly go over that formatting. I think too, Sam, was this cost the one adjusted for like extra inventory or?
yeah, I guess I broke down the total unit price like for a pack and then found the unit price. So that's why there's too many sig figs. But yeah, we definitely should have rounded it up to the cent.
Okay, so that might just be a formatting thing then. Okay, and then, how much are you paying yourselves, and how many of you are there?
Yeah, so there's 6 of us. So we just took like the average mechanical engineer's salary was 90 grand, and we did a 6-month term. So we did 45 per team member. So we ended up with total of 270.
$90,000 is the average.
Yeah.
Wow,
I
I'm
can
in the
I can
Yearly
I can
salary.
account that.
I can approve that, but I'm a little questioned, like, why 6 months? Do you guys think that you guys will be able to, finish the design and build of this thing? There's still testing that needs to be done. I think 6 months is a kind of
I think that was more for an entire semester, like realistically, for 6 months.
okay, yeah, because if I remember correctly, this 500,000, that's like for one like complete unit ready to go. And so like it's going to be a lot. You're going to definitely run into, I think 6 months is a little bit of a underestimate. To go with that term, how do you guys calculate manufacturing labor? That number seems awfully low.
Yeah, so we use like the provided like the cost, like the unit price based on the manufacturing method. So like machining and drilling holes and tapping holes. And then we multiplied by the respective like multiplier.
Okay. And so this is assumption that all of you guys or people likely your position are the ones also doing the manufacturing. You guys are not outsourcing any of the manufacturing.
Yeah, yes, in this case, yeah.
Okay. I don't know if there would be a reason to also maybe include facility costs, since even though you're not outsourcing, the facility costs are still there. That's part of the reason why I think your manufacturing labor ended up being so low, because you're essentially saying that we'll just do it when there's going to be more expensive processes. I don't know if you guys included the cost of anodizing, since you guys mentioned you're anodizing the rails. The cost of anodizing should be in there as well. That will cost a good portion of your manufacturing labor as well. So there just seems like you guys are missing some of the costs associated with that.
Yeah, on top of that, manufacturing labor also supposed to include the energy that you spend on actually manufacturing things and to run the machines, and as well as the tooling costs. If you need to buy one, or if you just need to use one, or rent in the place for like assembly, labor, and etc. etc. Also, your assembly is $25 only. That is very low. Were you doing it yourself?
Is that included in the salary?
No, we took the price, like the hourly wage for an assembly worker and multiplied it by our total assembly time. So it ended up being $25 per unit. It was like, I want to say it was like 45-minute assembly time per CSD.
So sorry, is this a 1 unit production cost or 100 units that you split per unit?
This is 1 unit production cost.
So, okay, then why is your assembly based on multiple CSDs that you split, then divide by numbers of that you have?
That assembly labor cost is just for 1 unit. So we took the assembly time that we got from like that Boothroyd Dewhurst the table, and then we multiplied by the hourly rate. So that assembly labor cost is for 1 unit.
Okay.
And if I remember correctly, the assembly time was 1,600 seconds, so about 20 something minutes, 26 minutes.
Yeah.
And just asking, I know you guys don't have it in the presentation, but I guess just for general assembly question, do you guys include torquing and applying Loctite as part of your assembly procedure?
Graber, did you?
So right now we do not have the exact torques required.
Oh, I
That's
know you
something-
guys, there's different torque requirements for each bolt, but I'm just saying, like, do you guys have that as part of your assembly procedure? Do you consider for having to torque down bolts to whatever the proper torque is, and then also applying secondary fastening methods like Loctite? Do you have that in your assembly procedure?
So for different bolts, are you saying that like for different bolts there would be like a different amount of time to tighten like one bolt versus another depending on its location and how secure it needs to be?
It's less about like the fact that different bolts would have different procedure, or just more about the fact that like you guys have that in your assembly procedure for all your bolts, because that's going to be a vital step and that'll take time, and that'll also cost money in terms of assembly labor and also having the materials for it.
Great, you included the assembly times for like all the fasteners, right?
Yes, I did. And each fastener, there was a column for fastening like each bolt or nut, and that is included.
Do you guys have the costs for Loctite and or like a torque wrench
No,
included in, or like any of your tools in that matter that you guys know you're going to use?
I don't think that was included.
Okay.
Okay, so before anybody else jumps in, we actually have exceeded the time by 15 plus minutes, and now we're actually eating into the next group's time. So we gotta cut it off there because at least the panelists have to jump into the next meeting. So if you guys want to, I'm really talking to Mark and Juliana here. If you guys want to follow up with these guys afterwards, via email, you are certainly welcome to do that because they still have a few hours before they have to submit their final design report. So all this stuff could be, I think I'm right in saying that, right? It's due today.
Yes.
Yeah. Okay.
We would.
Yeah. So there might be still a few loose ends that you might be able to help them tie up. But with that, we got to stop because we're going to eat into too much of the next group's time. So just very quickly, I want to thank you guys again for your presentation this afternoon and for the energy and creativity and grit and persistence you've shown throughout the semester. According to Jonathan Brooks, Mech 2 is the final boss of the mechanical engineering curriculum. So congratulations on defeating the final boss. Other faculty argue that it's Mech 3, so you might be up against another final boss next semester. But one of the bosses, at least, has been defeated. So congratulations on getting to the end of what we know is a very challenging and time-consuming class. So we appreciate all of your effort this semester. Thank you for that.
Thank you.
Thank you.
Thank you
Appreciate
for your feedback.
too.
Thank you, Dr. Trump. Thank you, Juliana and Mark, for your feedback.
Yeah, thank you guys.
You
Good job,
very much.
guys.
Very good. Okay, let me stop recording.